Talk about part 2 of measurement and resistance. In part 1 we were discussing about measurement of low resistance. Okay, the last method was potentiometer. Okay, so we are starting off with the potentiometer method. Okay, here you have your potentiometer. This is your circuit arrangement. We have a voltage source over here. Okay, we have our ammeter over here. This is your unknown resistance and this is your standard resistance. So what we are doing is we are finding out the unknown resistance with the help of standard known resistance. Okay, so we are switching the potentiometer terminals towards this to find out what current we are having. We know the voltage but we are determining the current. Okay, then we are connected to this one, then we know the value of current over here. When you know the voltage and you have determined the current, okay, then it is easy to calculate for this unknown resistance. Okay, it uses the concept of volt ratio box. Okay, this is your volt ratio box potentiometer. Okay, then we are having this as our analysis and the unknown resistance is given by this particular formula. Now we are starting off with a measurement of medium resistance. Okay, your medium resistance, what is a medium resistance? We have studied in part 1 that a medium resistance is something, a resistance value that lies between 1 ohm and 100 kilo ohm. Okay, so this is your medium resistance and we are going to measure. We have 4 methods over here: VI method, substitution method, Wheatstone bridge and ohm meter method. Okay, we are using we are now trying this volt meter method. Okay, it is exactly the same thing in same process and same circuit and same connection as that of the volt meter ammeter method which we were using to find out low resistance. Okay, the same exact analysis is done for the medium measurement of medium resistance as well. So we can say that voltmeter ammeter method is good for both measuring low resistance as well as medium resistance. Okay, here you can see, like we have studied in part 1, there are 2 cases in which you are having a meter close to your unknown resistance. Okay, then we are having this particular funda and this is your percentage error. Then we have here in this case your error is low when the value of unknown resistance is much higher than the internal resistance of the ammeter. Okay, same as that we have studied previously. Okay, now we have case 2 when voltmeter is close to your unknown resistance. Okay, here we have these analysis and your error is given by this particular formula. Then we are having approximate analysis given by this. Your error is low when your unknown resistance has lower value than the voltmeter internal resistance. Okay, then we are talking about optimum value of R when error is same in both cases. Okay, in if in case the error comes out same from both of these processes, then this is the formula of unknown resistance. Okay, only and only then your error is same. Okay, in case your error is same, only then you apply this formula, else not. Okay, then we have our substitution method. Here we have our rheostat, we have our voltage source, we have current passing through it, then the current is the deflection is given by this galvanometer. Here we are having a standard known resistance and we have our unknown resistance. As we are studying in potentiometer, same concept is used over here. Okay, you are having a standard known resistance. With the help of this you are trying to find out the unknown resistance because you know the voltage source is constant. What thing varies is the current. Okay, when you know the voltage and you can measure the current. Okay, with the help of galvanometer deflection you can measure the current as well. When you know the voltage and you can find out the current, you can easily determine the unknown resistance. This is the basic funda of substitution method. Okay, so this is your case 1. In case current in galvanometer is different. Okay, means if you are connecting this to this terminal and this terminal and you are having galvanometer deflection different in both cases. Okay, then I is given by I1 and this is basically your KVL equations. Okay, KVL KCL equations. So we are analyzing the entire circuit. Okay, since voltage is same, you know the voltage is same in both the cases. Okay, you are writing out the current equations but you know the voltage is still same. The supply is not going to change now, so we are equating them and we are finding out that unknown resistance is given by this particular formula. Then we have case 2. Okay, the galvanometer deflection is proportional to the current. Okay, so this is the formula we are going to use. Theta 2 upon theta 1 equals to I2 upon I1. Okay, then your unknown resistance will be given by this particular formula. Then we have case 3. In case we are having deflection equal. Okay, we are having same deflections, then this is your particular formula. Okay, same deflection means that your RT is equal to S, your unknown resistance is equals to standard resistance. Only and only then you will have equal deflection in both cases in the galvanometer. So this is what we are for. Now this is all for part 2, and part 3 I shall be discussing from here.